문 좀 닫아주시겠어요? Okay, so this is lecture 7. So currently we are discussing about process simulation for diffusion processes. So diffusion processes, atoms, dopant atoms are diffusing under high temperature. But in the last lecture, lecture 6, we have found that lecture 6, when you consider diffusion where electric field dependency is involved by introducing the term called drift. So we have found that actually the system becomes nonlinear. Okay, so let me just go to our lecture note. Okay, so in that non-linearity is quite important in our course, actually one of the most important topic in this course. So please recall our previous diffusion equation. So although the diffusion equation itself can be written in this form in general, because we have to solve an equation like this. So time derivative of our concentration is related with our flux of C, and there is a minus sign. That is general continuity equation for our dopant atom C. After that, when we make a 1D approximation, then in 1D case, that can be written as this form. So of course here FC means that of x directional component of this vector f. Then we can integrate over certain volume. So for example, in the case of this case, we can integrate from x minus half up to xi plus half. This is corresponding to the midpoint between xi and x minus 1, and this one is corresponding to xi and xi plus 1. So we can make such kind of integration. Then now this is corresponding to the time derivative of our dopant density, and it was integrated, and the length of integration range was delta x. That's the reason why we have delta x. And here we have some terms originated from the integration of this minus round fc over round x. So now we have this. And now we have spent our lecture hours, previous lecture 6, for deriving this kind of expression. So depending on the polarity of our dopants, we have a different sign here. But anyway, when you have a look at this flux term, then you can immediately find that there is some dependencies on C, of course, but there is also a dependency on electron density. Then this electron density n was a nonlinear function of C. So in our charge neutrality approximation, then we wanted to say that minus n plus p, and eventually dopant density, so net positively charged dopant ions, their sum should be 0 under the charge neutrality condition. Why? It is just an approximation, but still we wanted to take this approximation. So when we have this kind of approximation, we immediately find that this is more or less related with C. So from this expression, now we can find that N electron density is a non-linear function of our dopant density C. This is exactly the same statement shown here. So now we understand, although we are talking about quite a simple diffusion phenomenon, still we have a nonlinear system which when we write down in terms of concentration C.
지금 여기서 이 이퀘이션을 보통 continuity equation이라고 부르거든요.
You are right, yes. So this is just a continuity equation. So there can be many different continuity equations. Actually, so just to write down, continuity equation in its general form is just given by this one. There is certain scalar quantity, so usually for density, and this density is balanced by minus times gradient of a certain vector field. This is a vector field, and this one is called as flux of that physical quantity. So this is density of something x, and this is flux of something x. This is in general called as a continuity equation. So which continuity equation we will consider in this course? First one is dopant. So for example, in the case of arsenic, we can consider arsenic concentration. Time derivative of arsenic concentration can be written as flux of arsenic dopants, for example. Also, we can consider, instead of this arsenic, we can also consider this kind of thing like boron. Okay, also here we can consider boron. Anything can be inserted in this point, and this is related with the dopant. However, we wanted to also solve another one like electron. In the case of device simulation, actually what we solve is simply this form. So minus times flux of electron. Let me just read it. So time derivative of electron density is determined by flux of our electron. If electrons are escaping from certain position, let's say that, then this quantity becomes positive. So then what will happen? The net number of electrons will decrease. So that's the reason why we have a negative sign here.
Diffusion equation이 사실은 continuity equation인가요?
The reason why we have called it as a diffusion equation is the flux shown here, for example, arsenic, only contains diffusion of arsenic atoms. Okay, so are you with me? So if we consider not only diffusion, also, for example, drift of arsenic atom, as we discussed right now, then it is no longer just a simple diffusion equation. However, still I want to say that this is still called as a diffusion equation because in this case, the major physical phenomena is merely diffusion, and drift is a secondary impact in this case. Okay, so that's the reason why still we call this effect as a diffusion of dopant instead of drift and diffusion of dopants. But please note that basically what we solve is actually continuity equation. Because why we are solving continuity equation? Because we are interested with the time derivative of a certain physical quantity, density related quantity. If you are interested with this kind of quantity, then actually the continuity equation is the equation for your choice. Okay? So if you wanted to the time derivative of electron density, then you must solve electron continuity equation. If you wanted to know the time derivative of your arsenic density, then you must solve also the time derivative continuity equation for your arsenic atom. Of course, so your question was really interesting, and let me ask this question. Then, is this the continuity equation the only form for specifying such kind of density related term? The answer is actually not. No. For example, we can think about this one. Let's say that this is kind of a road, and there are many cars. So there are so many cars, and if you wanted to calculate the net increase of your cars within certain, for example, 1 kilometer long interval, then what you can do is just count the number of incoming cars and counting the number of outgoing cars. If we have just a unidirectional car flow, then for example for 1 minute, if there are 10 cars incoming and 9 cars are outgoing, then what will happen? Given 1 minute, then you will have a net increase of 1 car. That is the one specified this continuity equation. But unfortunately, let's think about this case. This is quite suitable for your continuity equation. But instead of that, now think about the, so if we are interested in the number of cars here, then it's okay. But let's think about this one. There is a trap for LEDs. So there is LEDs and they are moving. And there is a shallow trap. We wanted to capture as many as possible cats and LEDs, and they are moving. They are moving, and we wanted to know how many LEDs are captured in this trap system. So number of LEDs. Then can we consider, for example, let's say that now I wanted to just take the incoming number of LEDs and outgoing number of LEDs. Then that is related with the change of LEDs captured by this shallow trap. So are you with me? This is not suitable description. So you have to understand this is not a good description. If we have, for example, 10 more LEDs and 9 less LEDs, however, that doesn't necessarily mean that one more LED is captured by this system. So are you with me? In order to capture actually the net increase of our LEDs in this case, then you must consider how many LEDs are actually captured and how many LEDs are jumping and eventually escaping from this one. This is nothing related with this kind of behavior. This kind of behavior, flux and its divergence, it is related with real space movement. So cars are coming and outgoing. But you know, in this case, this is nothing related. This horizontal lateral direction movement is nothing related with capture and release of our legs. The only important motion is their vertical motion. Oh, one leg is falling down and one leg is jumping and sufficiently high, then it is escaping from this level. So what we wanted to say, or what I wanted to say right now is, when we try to describe the change of number of legs in this case, this is nothing related to such kind of thing. Calculate the flux over legs and minus, it's not. Actually, that should be balanced by some probability or some number of let captured left and escaping left. So this kind of direction is, if this is x-axis and it is just local in the x coordinate. In x coordinate, it is just jumping same x position and no change in its x coordinate. Okay, so are you with me? So, although your original question was not directly related to this one, but I wanted to say that his question was quite important to our overall lecture progress, because once we wanted to know the time derivative of a certain physical quantity, and in this case, we have to introduce any kind of description for that number, that time derivative. And usually, if real space movement called flux is available, then continuity equation is a good choice. However, if that is not available, instead of that, the local change of status is important, then we have to consider other ones. And typically such kind of thing not related with, can you say, uh, not related with the flux terms, if there is nothing, and just to consider some capture and emission rate, then this kind of equation is typically called as a rate equation instead of a continuity equation. Continuity equation. So in reality, we have to consider both of them. So continuity and rate equation, because so when you consider such a certain system, there can be also physical movement or positional movement and change of status. So okay, so are you with me? So the typical example what I wanted to show you in every semester is like this. So think about the number of persons in Republic of Korea. So let's say that this is Republic of Korea. Of course, here we have some um, other island. But anyway, let's consider this is the amount we are considering. Then if I ask you this question, how many, today is September 18th, then what will be the number of persons in September 19th? Can you predict, or can you write down the change of Korean population within one day? Then if we follow the philosophy of continuity equation, then what you can do is just connecting the incoming airplane passengers and counting the outgoing airplane passengers. So of course we have other means like some ships and certain kind of thing, but anyway, if we consider just traffic, overseas traffic, then we can consider the change of Korean population for one day. is it enough for our description? So this sounds reasonable, but there is one very important effect which was not considered in this kind of philosophy. The missing effect is birth and death of internally happening in this Korean land of Korea. Okay, so in order to consider the or in order to predict the number of persons in Korean Republic of Korea, then we have to both consider this kind of flux related terms and also rate related terms like birth and death. So in general, you have to solve certain terms like time derivative of such kind of density related term is written as flux related terms and plus and rate related terms. We must consider those kind of things. Okay, so are you with me? So even in the case of this dopant diffusion case, so later we will see that not only flux but also rate is quite important for our discussion. Okay, so although his question was not directly related to this one, but thank you for your interesting question. And yes, now let's come back to our original discussion. And now we understand, although we are considering quite a simple system, considering one species and yeah. However, if we introduce the drift effect into our consideration, then now it becomes much more complicated because now the system becomes a nonlinear system. So then, okay, anyway, we wanted to express it as AX equal to B system, matrix equation system. Then maybe we can solve it, then calculate the X value. But you will immediately find that your attempt to express our previous equation, so previous diffusion equation, in terms of AX equal to B immediately fails because there occurs like n, and n is still a nonlinear function of c, but ax equal to b when we have a c vector as a solution vector, then this A is linear matrix and ax equal to b can generate just a group of linear combinations of our C values. So this kind of nonlinear effect cannot be considered this AX term. Okay, so for example, C1 plus C2 two times, three times, it can be expressed as just 2, 3 times C1, C2. Okay, this kind of linear combination of C1, C2 can be easily expressed as this matrix vector multiplication. However, if we have 2 times C1 square times 3 times cube of C2, then it is impossible for us to express it as this form. Well, the only way we can do is C1 and here C2 square. But this is not available because this value is just dependent on our solution vector, so no way to calculate it. So now we understand when we introduce a slight nonlinearity, whether that is so severe or not, Anyway, if the system is slightly deviated from the perfectly linear system, then our previous attempt to solve the solution vector from ax equal to b drastically fails. So we must find out another way to uh, solve this system. Please note that in our previous simple problem, the discretized form was so simple and it was really a linear combination of c quantities, c at x over I plus 1, xi, and xi minus 1 were combined with given coefficient. So it was not that difficult to express in terms of ax equal to b. So now I wanted to say that the most important one is, in this case, is the nonlinearity. So we cannot solve the problem because it is nonlinear. Then how can we solve a nonlinear problem? So I have one example taken from our charge neutrality condition. So charge neutrality condition, what was it? So here we have a left hand side term and here we have a right hand side term, and left hand side term just describe the number of positively charged particles, and right hand side term contains negatively charged, so negatively charged dopant ion and also negatively charged electron. Then here we have another condition which is valid only at equilibrium. But it's okay because we have already introduced this kind of approximation. So now by combining these two equations, we can calculate its analytic solution. For example, I'll consider this is a given number and this is a given number. Instead, both of electron density and hole density will be regarded as unknown variables. So one equation and two unknown variables. It's not good, but fortunately from the second expression, so-called mass action law, now we can express hole density in terms of electron density. Then please insert it. Then what you can get is now simply given by this form: nd plus minus na minus plus n intrinsic carrier density divided by n equal to n. Are you with me? Then we can multiply n to right hand side and left hand side all together. Then this is gone, and here we have a square, and here we have n. So simply speaking, now we can have a quadratic equation for n. Of course, we know the analytic solution of this system, so you can easily calculate n. So because we memorize the solution. However, instead of using the known formula, just calculate n with a numerical method. So that is our goal. We can easily introduce more and more complicated equation than this simple equation. But if we have a general approach to solve this equation, then we can apply to even more difficult equations. So this is a Newton method. I have tried to explain it step by step. So the first step, we assume an initial solution and none. Okay, so of course there is no guarantee that your guess is the right one. Of course, more or less you will be will be long. So therefore, for sure, we can say like this. When we insert n not in the place for n, then of course you wanted to have this 0, but unfortunately it's not. Your value will be different from 1. So let's consider a simple example. You wanted to solve this one. What is the answer? You understand 1 is the answer. However, let's assume that you are not much educated. Then you must guess the answer. Then somebody say that, okay, maybe number 2, 3, 5, 100. Anybody can make any number. Then what will happen? Just insert it. Then 4 minus 4 plus 1 equal to 1. So which is not 0. So you can understand this number 1 just to indicate the failure of your initial guess. If this number is quite close to 0, then you are happy and you are close to the real solution. And if this number is quite large, like 100 or 1000 or 1 million, then it means that your solution is far from this good solution. Okay, so anyway, now let's assume that at first trial your solution and not is not the real solution, but you are not frustrated. However, we assert that, okay, currently our n not is not a solution, but I will improve it. So by adding certain amount of correction or so-called update, then we can generate improved solution n1. And now we believe that although n0 was not a good solution, but when we correct it, then now this n1 is the perfect solution. That is our hope and our assumption. Okay, so of course there is no guarantee that our assertion should be satisfied. However, anyway, we can do such kind of a thing. Then let's just insert it. Now we assert that when we have n1, this is actually 0. Previously it was not 0 because n not was used. However, now when we use n1, now we have exactly 0. Then we have two equations and we can take the difference between them. So taking the difference, then we will have this form. So what happens? So taking the difference between this and that, now you will have n1 squared minus n not squared, and this term is shown here, and just the difference between n1 and n not, and you are here, and finally the right hand side term 0 and r0. So you have this form. Now now when you have a look at it, looks quite good. If we can solve this equation, then what does mean is n not is given because we have number 2 or 3 or 5, and not they are given, and also r0 r not is given. So now we have unknown variables like here n1, n1, and n1. If we can solve this equation for n1, then we will get the perfect solution. Or for example, if we can solve the equation for this update or correction here, then we can solve this equation. Then we can calculate the n1. But unfortunately, so please have a look at this line. Unfortunately, we cannot solve the above equation because once again, here we have n1 and n1 again. This is once again a quadratic equation for n1. So if we can solve this equation, then actually we will solve just the original equation. We cannot solve any kind of nonlinear equation. That's the reason why we are developing this kind of method. So therefore, since we cannot solve a nonlinear equation, still this equation is nonlinear equation, we cannot solve it. However, the last one is the important approximation. Now we make an approximation. Instead, we can solve the following approximate equation. What is the approximate equation? When you have a look at this one, we treat this update and update as a unknown variable. Now we have update and update, and this right hand side term was just evaluated, and this is the given constant. We know it. The only problem is related with this one. Here we have n1 plus n naught. Since it contains n1, we cannot solve it. But in this approximation, we will say that, okay, I will just use just 2 times n9. Of course, I wanted to emphasize that solution of this equation n1 minus n0 is not perfect one. So when you calculate n1 from this one, then your n1 will not be a perfect solution. Of course, it is because you have introduced an approximation. But we hope that this approach is much better than nothing. So that is our hope. Unfortunately, when we calculate n1 minus n0 by solving this last approximated equation, then our solution is not exact. But anyway, from n0 and its update quantity, then we can calculate, although inaccurate but updated n1. Then from n1 we can calculate once again n2 following the same procedure. So starting from n0 and not, which was quite awful, then we can move to n1, improve, and n2 much better, and n3 even better. If we just take this kind of iterative improvement, then finally, for example, after 20 iterations, then maybe that solution will be quite close to the real solution. Of course, there is no guarantee, but that is our hope, and we wanted to do this kind of procedure. So are you all with me? Okay, so this procedure is called as Newton method. The Newton method is the powerful method to calculate the numerical solution of any nonlinear equation. Okay, so now you have your homework. number 7, and please calculate it or do it in this Wednesday. Only that this is next lecture. Calculate electron density under the charging neutrality condition. I mean that please solve this equation. So please solve this equation. That is my homework. Of course, you must know what is intrinsic carrier density and what is net dopant density. So, in order to solve this equation, I have prepared one expression for you. Well, where can you find the expression for an intrinsic carrier? So, I'm not so sure. So have you already considered this intrinsic carrier density before? Okay. Oh, sorry about that. So previously we have already introduced the expression for intrinsic carrier density as a function of temperature. So please use this expression and consider 3 different doping concentrations. So 10 to the 20, 10 to the 18, and 10 to the 16 per cubic centimeter, and 2 different temperatures. So of course, this is so simple equation. You have a quadratic equation and their coefficients are given. So from this expression, you can calculate the one coefficient, and you can calculate another coefficient from this four given number, 10 to the 20, 10 to the 18, and 10 to the 16. Then please make a comparison between the analytic solution and your numerical solution. So that is my first homework. So are you all with me? Any question on this homework number 1? Okay. So, please.
혹시 루턴스 워드 그 비전형 상태에서 성형으로 어프로치메이트 해주실 때
Okay.
N1 플러스 N0를 EN0로 바꿨었는데 일단 쓸 수 있는 이니셜 값을 쓰면서 어프로치메이트 해주시려고 저렇게 그려놨어요.
Okay, so let me just reiterate his restate his question. So, that is a really good question. So his question was, okay, this second last equation. This equation is exact one, and this last equation is approximated one. And what is the difference? The difference is here we have a certain coefficient for, or certain in general certain term, and that was just approximated here 2 times n0. So you can find that n plus n naught was approximated as 2 times n naught. And his question can be restated as, is there any general rule to convert from this seemingly nonlinear term or seemingly complicated term to seemingly simple term? Is there any general rule? That is a little bit generalized his question. So in this case, we just simply say that n1 and n0 are not that much different, so we can make it. But in general, we have to consider more general expression. Now, usually when you, for example, thank you so much about this one. If we have, instead of this secondary term or second order term, let's say that our equation now becomes this cubic equation, then what will happen? Then what we have to do is cube over n1 minus cube over n0, and we must express it to n1 minus n naught and something. So something I don't remember anymore. But you know, if we have this kind of expansion, then what will happen to this guy to make an approximation suitable for this kind of solvable linearized equation? So his question can be answered by this way, in my opinion. This generalization slide can be an answer to his question. So let's say that instead of a given equation, but now consider a general function of phi, so f of phi. F of phi can be anything, any known function. So now let me just follow the slide. Then as we did with n naught, we just say that this temporal solution phi naught, this is not a good solution, therefore we have a non-zero value when we evaluate it. So our goal is to find such kind of the real solution which satisfy this number. So that is our goal. And however, we assert that instead of phi naught, if we add delta phi, then once again hope that this phi 1 is good enough. So as we did, then what we can do is now phi 1, with phi 1, the solution is found and it is simply given by this form. Okay, so are you with me? Because phi 1 is defined as phi not corrected or updated. Then this one is difficult to solve. If we can solve this equation, then we can immediately calculate the phi 1. However, this is not an easy task. So my answer to your question, Mr. Jones' question, is this one. Linearized form or linearization is the way we take. So now this difficult nonlinear function f is approximated as just f evaluated at f naught plus df over d phi evaluated at current value phi naught times delta phi. So are you with me? So this is just the first order Taylor expansion and linearization. So now of course we can introduce more and more terms like something like second order derivative evaluated at phi naught and times delta phi square, blah blah blah. We can introduce higher order terms, but all of these higher terms introduce once again non-linearity. So it's not good for our solution, or not beneficial for ease of calculating something. So we neglect any kind of non-linearity and takes just linear term. Then now by applying the Taylor expansion, the first order Taylor expansion, linearization, now we have this form, and from our assertion that should be 0. Then now we take this delta f as an unknown variable, and this derivative, first order derivative, can be evaluated. Why? Because we know the form of f function and phi naught is given, so evaluation itself is available. Also this function value itself is also available. So means that if we know the function value and its first derivative value at given f naught, then we can estimate the update vector or update delta phi. So the update, oh sorry, I made mistakes. This is typo. The updated delta phi can be calculated by solving this equation. So once again, this is a function value and this is first order derivative. And both of them are available. So now, since your question was so important, so let me just come back. Then now let's try to apply our specific example. In this case, our phi and n can be written as n squared, and what was it? Minus, I'm not quite sure the sign of the term here. Oh, here we have minus doping density and minus. Okay, so just minus doping density and the plus minus Na minus n and int square. It was the function f. Then what we have to calculate is function evaluated at n naught, and it is given by n naught square minus something with the doping density and naught minus n int square. You can easily calculate it. Okay, so then another one is now first derivative. Then first derivative can be calculated 2 times n minus n d plus minus na minus. So when we evaluated f and not, then now we have this form. So simply speaking, in this case, delta n in our previous example can be obtained by, so 2 and 0 minus nd plus minus na minus times our f and naught. That will be the solution of our update delta n. Okay, so Mr. Jung, are you with me? Okay. So how about other students? So we are now talking about the generalization of this Newton method. So not only for this secondary equation, for example, instead of this second order term, we can easily say that now this is a cubic term, but it's not that difficult. So everything is just the same as before. We can just evaluate this function value, and now this first derivative term now can be 3 times square of n naught. That's it. So generally we can just say that only required thing is twofold. One is evaluate the function value and also evaluate the first derivative. Then you can calculate the update.
이니셜 솔루션은 보통 어떤 식인가요?
Okay, so let me restate his question. His question was then good. So once we start from phi naught, then we can go to phi 1 and phi 2, and we can just increase the index. Then we can approach to the realistic solution. Then his question was, then it seems that phi selection of phi naught seems to be quite important, but how can we calculate or guess this phi naught? It really matter of experience. So you need some skills or some previous knowledge on the system. So, so let's say that, for example, let's come back to our system. I wanted to ask you the question. So, if you have to solve this equation, then what will be your initial n value? So, okay. So one possibility is intrinsic carrier density, but that will be quite poor approximation. So if you are educated, then you will find that this one is really good in starting point for your n not, because you know donor density is more or less corresponding to the electron density, net donor density. So that's the reason why you will find that this is much better. So now think about this case. Well, I start from intrinsic carrier density, and or I start from donor density. Which one will give you better convergence behavior? How many iterations will be required to get a good solution? Obviously, when you start from this one, it means that at 300 Kelvin, you start from 10 to the 10 per cubic centimeter. And let's say that you have 10 to the 18 per cubic centimeter donor density, then it will take forever. So your electron density will be of course increased. However, it will take some iterations to arrive the solution of 10 to the 18. But if you take this second approach, so since you are educated in previous lecture course, okay, and not simply given by ND plus, then just one or two iterations, you will get perfectly good solution. So your question was a really good question. In this Newton method, the important thing is, since everything is just mechanical, so when you have f, then everything is just automatically available. Function evaluation and first derivative evaluation. Only with these two calculations, you can calculate the update. So there is nothing. Everything is just given. Only thing we can improve this procedure is, this initial solution. Clever guy will introduce a good initial solution, and dull guys will introduce the solution initial guess far from the realistic solution. That is the difference. Okay. Anyway, that was a really good question. Is there any question about this contents? So the first homework was related with Newton method. And now the remaining part of our lecture will be devoted to the Newton-Raphson method. Newton method was applied to a single variable problem, one variable, and when we have multiple variables, 2, 3, or 100,000, in our case we can easily have 10,000 or 100,000 unknown variables, then we can solve this complex system also with our Newton-Raphson method. So extension to the multivariable cases, extension of the Newton method to multivariable cases, that is called as Newton-Raphson method. So let's consider the simplest one, just two unknown variables. Now we have x and y. They are unknown variables, and we must solve these two equations, f and z. And both of them or one of them are or is nonlinear function. Okay, so then overall system is a nonlinear system. Then now we proceed exactly the same one, but although quite boring, so let me just do it. Here I have also one typo. Again, your initial guess x naught and y naught do not satisfy the equations. So there is no hope that in general we have these two numbers or these two equations satisfy. So following the same procedure for Newton iterations, now we say that although x naught, y naught, they are not good, but x1, y1, they are good. So now we can write down. Then what will happen? If we have x naught plus delta x, y naught plus delta y, then we can also introduce linearization, but not only for x, not only for y, but we can make the linearization with respect to these two numbers. So simply speaking, I want to say that x naught, y naught, this is function evaluation, and instead of first order derivative, now we must take the partial derivative with respect to x and delta x. Also, we wanted to introduce first order derivative, partial derivative with respect to delta y. Okay, so are you with me? So previously, when we had just one single variable, then now we must consider this one, only this one. That's it. However, now we introduce a second equation or second variable. So second variable, for this second variable we have additional terms. So, this is nothing but linearized f function, and this second line is corresponding to linearized g function. So function evaluated, oh, I made another mistake, so sorry about that. So here here we have so sorry about that, I make many typos. And in the linearized form, we can say that f is approximated, and also g is also approximated. And please note that here what you have to calculate is function value and partial derivative, and partial derivative and partial derivative. But you can understand the number of function evaluation and number of partial derivative are not perfectly matched. You must evaluate the function twice, and you must calculate the first derivative 4 times. Why we have to calculate 4 times? Because what we have to do is now taking a partial derivative of a certain function with respect to a certain variable. Here we have a variable, and here we have equation. How many equations? We have 2 equations. How many variables? We have 2 variables. So therefore we have to consider 2 by 2, number 4 iterations. Instead of this number 2, let's say that now we wanted to evaluate 3 equations and 3 variables. Then what will happen? In this case, we must consider 3 equations and 3 variables. So calculation of first order derivative should be done in 9 times. Then how about function evaluation? Function evaluation is only related with the equation number, so therefore we will perform only 3 function evaluations. So are you with me? So now let's say that now you have n equations and n unknown variables, then what will happen? Your function evaluation will be required n times, and your partial derivative evaluation will be required square n times. Okay, so then is there any way for us to make it simple and compact? Yes, we have it. So now let's express the previous equations in the form of ax equal to b form. So please have a look at these two equations and please try to express them in terms of ax equal to b. Then, sorry about that, this is still 0 and 0. Then first of all, we must introduce the x vector. Then now the solution vector x can be written as this one. Now delta x, delta y is taken as the solution vector, and we wanted to fill this A matrix. This is corresponding to X vector, and here we have A matrix, and A matrix takes the coefficient for delta X and delta Y. Please find that. Here we have coefficient for delta X, coefficient for delta Y. Also another coefficient for delta X and another coefficient for delta Y. So let me just do it. X, and please check whether I make any mistakes when I write down in this expression. So when you have a look at this matrix vector multiplication, then when we evaluated this matrix vector multiplication, the upper part, the first row, will give us this upper one, and the second row will give us this second row. So are you with me? And the remaining thing is, here we have f and f, so it can be written as, once again, f evaluated at current solution and z evaluated at current solution. Wow. So when we revisit this form, then what is the update vector? Then we just take delta x and delta y as an entries of update vector. Please note that previously we considered just concentration C as entries of our solution vector, but now it's not. It's not x, y. We just calculate update for our solution variable, and A matrix can have this form as I shown here, and the remaining thing is the function evaluation. The evaluated function is now b, but unfortunately I have made another mistakes here. We must have overall negative sign here, because here we wanted to make ax equal to b terms, so we must have minus sign here. We can repeat this equation, this calculation procedure again and again to get the realistic solution. So now please do your homework program. Here we have a very simple 3 variable cases. 1, 2, 3 variables and 1, 2, 3 equations. Then what you have to do is also evaluate this A matrix and our B vector. Please note that here we have a minus sign. Then what you can do is just to evaluate and take the negative sign. Then you can calculate this 3 by 3 equation A and your 3 by 1 update vector, and now you have your 3 by 1 B vector. Then by solving this matrix equation as usual, then you will get 3 by 1 update vector, and using that update vector, please update your solution. Then you will get the answer. So, as one student pointed out previously, initial guess is quite important. Here, I'm showing you two different solution procedures. So one guy start from a null vector 0, 0, 0, 5, 1, 5, 2, 5, 3, or 0 at the beginning, or 10, 10, 10, 5, 1, 5, 2, 5, 3, or 10. Then what happens? So starting from 0 and 0, after 1, 2, 3, 4 iterations, then you can find that this number, this number, this number, and this number, this number, this number. Already between the third solution and fourth solution, the difference is quite small. So it means that we are now quite close to the numerical solution. But in this case, we start from 10, 10, 10. Then now it is reduced and reduced, reduced, reduced. After 4 iterations, we are quite much off from the numerical solution. Of course, if you wait for more iterations, and eventually you will be there. However, it will take some more iterations, and these iterations is related with computational cost. So please try to find out reasonable initial guess. Okay, so then let me wrap up today's lecture with problem number 2. Please solve the previous example and not starting from only 0, 0, 0 and 10, 10, 10. Please make your initial guess. Then select various initial guesses and measure the number of Newton iterations. Then, what is the number of required Newton iterations? Then, the convergence criterion for your iteration is maximum absolute update smaller than 10 to the minus 10. Please use this one. For example, what does it mean? So between 3 and 4, although they are quite close, but you can find that the difference between 1, 9 and 2, 2. So the difference is like 0.000 and 0.3. This is the difference between third solution and fourth solution. So this is still orders of 3 times 10 to the minus 5. But you can expect that when you go to fifth one, the difference will be much smaller, and sixth one much smaller. So please stop your iterations when the number or difference between your unknown variables is smaller than 10 to the minus 10, which is quite small because our solution is more or less 0.7, 0.2, 0.4. So 10 to the minus 10 means that quite acceptable quality as a numerical solutions. Okay, so are you with me? And any other question about this homeworks or lecture contents? No? Okay, then if you are all satisfied, then let's wrap up and yes, then see you this Wednesday. Bye.